data lake and platform as a service. I deal with Hadoop and other big data technologies. I specialize in Hadoop operations, containerized deployments, Ambari and Cloudera stacks, and developer operations, DevOps actually. So this is our agenda for today. First of all, we are going to get a small introduction on big data ecosystem, why we need an ecosystem, and why there was a need for Hadoop. Then we are going to go ahead and go through the goals and goals walkthroughs. Then I'm going to give you a brief introduction of what data lakes are, and introduction, a very brief overview of the Hadoop distributed file system and how your data gets stored on that actually. So one person has left. Feroz, should I wait for that person to log back in? Hello, Feroz. Okay, anyway, I'm going to go ahead and continue the course. So this is our agenda for today. So let me start off by talking about data. In our current scenario, the world we live in, we produce petabytes of data every day. It's said that we produce more data since last year than we did all of eternity, as in from the beginning of humanity. So this is a very small pictorial representation of the data that is created every minute of the day. You can see all the likes and shares and Skype calls, book cabs on Uber, or order products on Amazon, post content on Reddit, Facebook, anywhere. So whenever you do something, interact with someone, or you do some operation on the World Wide Web, it gets persisted somewhere. Everything from your IP, your login credentials, anything, whatever you do gets logged somewhere or the other. So all this data gets has to be stored somewhere. So previously we didn't have this challenge of storing this much data. We only used to keep data which was necessary, which was mandatory for us, like login credentials or transaction details or such and so and so forth. But nowadays storing has become very cheap, so we don't let any data go waste. We make the most out of it. Nowadays we even record the games we play on our phones. How much did we play? Did we spend any money on the game? How many hours do we play every day? All those things are recorded. We don't let any data go to waste. But the thing is, let me give you a brief introduction of what big data is. So as I said in the previous slide, the amount of data keeps increasing. Along with that, the challenges also are varying and different, and new challenges come every day. So big data is a data set so large it becomes difficult for traditional database management tools to handle it. It is very similar to the traditional RDBMS or small data analytics, only that there are few additional challenges, such as storing the data, managing it, multi-server architectures, distributed architectures. There's no central server where we process all the data. It's all distributed processing, mostly massively parallel processing, and handling bottlenecks, and making sure that your system is responsive and the hardware requirements are very different for big data compared to traditional databases. Also, traditional databases, we used to store data which was only essential. Now, in the advent of big data, we store everything. We don't let anything go to waste. So that's a very small tidbit about big data. It's very similar to small data, but just that it's the volume is very high. So along with that comes a few challenges. In data access, how you're going to access the data, how you're going to clean the data, and how will you organize this data. So as I just said, traditionally we used to persist the data which we need. Right, since now we are persisting whatever we get, all these becomes challenges. So let's say that we have some machine logs, and we need to categorize them, we need to sort them, and we need to place them, and we need to clean them such that we make sense of it later on. For example, there is a log of a server, and we don't need majority of it, right? But we still store it. But later on, when we need actionable insights from it, we need before we get the actionable insights from it, we need to clean it properly. We need to get rid of all the noise. We need to look at the stuff that actually matters. So those things are challenges, and when it's on this scale, petabyte level scale, the challenges are immense. Also, challenges come in storage and management. Traditionally, if you take example of Teradata, they used to charge a few years back. They used to charge $1 million per year for 1 TB of storage. So that is, when you consider it right now, that is laughable actually. So the scenario of storage and management has changed with the advent of big data. We need to store lots of data, and we need to store it cheap. We cannot rely on very expensive hardware to manage and store our data. Also, in big data, and especially in data lakes, you have multiple services running with various architectures, and these run on multiple servers, and all these run in a data center. For example, if you have a 1,000 node system where you're going to store the data, someone has joined. Welcome. So when you have, let's say that you have a 1,000 node system and you need to store the data. In case of a data lake, you'll have multiple. Let's say you'll have multiple. Second. Okay, you have multiple services running. For example, you have HDFS Yarn and Hive, all these things running, and these have multi-server architectures. We need to manage this as in a central location where we can keep track of what is running, what is not running, are there any faults, all these things. Though that adds to the challenge. And also in big data world, as I said, we don't let any data go to waste. So we can get structured, unstructured data. As I mentioned before, for example, server logs. So that is unstructured data. But if you're going for transaction logs, those are structured. So you need to handle both. So there are added challenges to that as well. Also, the landscape is, big data landscape changes very fast actually. So new tools come out. New frameworks come out, and someone figures out a better way to do certain things. So as the ecosystem grows and evolves, there are added challenges to keeping track of all these things. And finally, one of the major challenges is the skill gap. Actually, people who right out of college know databases and all those things, when they come into the big data world, they find it very difficult to cope up because the terminologies, the way we handle things, uh, and the architectures and the frameworks are entirely different from what traditionally we used to use. So it adds to the challenge, actually, the skill set, the skill gap, actually. So if you have any doubts, please message me, or you can unmute yourself and ask the question. I'm going to go ahead, assuming that you have no doubts. So there arose a need for a proper ecosystem for big data as the data sizes grew large. In the past decade, the cost of storage has gone down tremendously. I remember some time back, it was very expensive to have even 1 GB of storage. Now you can have that on the palm of your hands. You can have terabytes in your hand, actually. So the cost of storage has gone down. The cost of computation has gone down. The bandwidth cost also has gone down. But one of the most costliest thing is network IO, or network access. So that is what people try to minimize nowadays. RAM is cheap, CPU is cheap, bandwidth is cheap, but network IO is very expensive. Can lead to a lot of bottlenecks, can lead to a lot of headaches in the future, actually, if you don't take care of network IO. So also people couldn't scale properly in the traditional databases. So we are talking about the need for an ecosystem. So first is the 4 points which I mentioned: the cost varying, storage and CPU and bandwidth cost went down, network IO went up, and also that big data cluster should be scalable. Let's say that I have a 100 node cluster, and tomorrow I decide that I'm going to increase my capacity. I should be able to add nodes on the fly. I shouldn't. It should not be that I need to reconfigure everything and start from scratch for adding 10 nodes or 50 nodes, like that. So also there was a need for common infrastructure. For example, in the telecom world, previously everything used to be hidden. Every company used to have its proprietary tech, and they used to work only on that. And people working on it would get expertise on it, and the company would depend on them for everything, and the people would depend on the company because they work only on that. And there was a dependence on each other. There was no common infrastructure. And now, as you know, computers are very cheap. It's getting cheaper and cheaper. All these points led to a development or a need for an ecosystem of big data tools and frameworks, which led to the rise of Hadoop. And let me very briefly explain how data cost and culture vary for traditional databases and big data, actually. So in traditional relational databases, you had a strict schema. You could store data only within that schema. For example, the classic example, student table, all those student IDs, all those things. But in big data, you can have any types of data. You can store Twitter feed. You can persist your Twitter feed. You can have videos, audio. You can have server logs. You can have search logs. All those things can be stored on the big data frameworks, which we are going to talk about. There's no schema, actually, in the big data world. We need to persist everything that we get. Also, as I mentioned before, the cost. Teradata used to be $1 million per terabyte, and now it's like almost nothing for a terabyte right now when you consider corporations. So cost for traditional databases, it is very expensive. You need to buy custom hardware, you need to have blades, or you need to have certain HP systems or certain Dell systems. The vendor, or let's say MySQL, or someone would say, okay, you need to have these many servers running this configuration with this much, bandwidth and all those things. A lot of it was getting very expensive. It is very expensive. So the thing with big data is it can run on any hardware. It can run on your laptop. It can run on your home PC. It can run on servers. It can run on anything. So this changed the landscape entirely. So you are not dependent on any hardware vendor or expensive hardware. So in order for people to learn big data as well, they could run it on their laptops and run small jobs with it. Previously, which was not possible. You need expensive hardware to run all these things. Also, the culture of reporting has changed with the advent of big data. So traditionally, we used to persist the data. Let's say that some bank transactions. You persist the data on the database. Then after some time, you come back and you look at it. Okay, these many people came into my bank at this time. These many people transact. There were these many transactions. All those things. So we used to use rear view reporting. We never used to take actionable. We used to take action. We never used to take action with the data at hand right now, which has changed recently, which has changed right now. We take action whenever possible. We take immediate action. We get more insights. Things like stream processing using Storm or Spark. You can take instant action. Let's say that some topic is trending on Twitter. So you want to do something about it. You want to run a marketing campaign. So you can run it instantly rather than waiting for 1 week. Then going back and forth. Let's do this campaign and run the campaign, which is pointless actually in this current world. So you need to take action fast, and you need to take decisive action as well. So that is these are the major differences between traditional and big data, tools and ecosystem. Moving on, I'm going to introduce a term called the data lake. As you guys must have heard of the term data warehouse, which is currently replaced by the term data lake. Data lake is, you can call it a data. You can call it a dump. You dump every data you get. You can dump the logs. You can dump any sort of data, pictures. As I mentioned in the previous slide, any sort of data you can dump into the data lake. For example, I have a website. I want to keep track of who is visiting my website, of IPs, the amount of time, what do they click on, which, how did they navigate. All these data I can dump onto my data lake. I don't need to use it right now. I can use it right now, but I can keep it, and later on I can just clean the data, use the data which I need, and let it be that, let the data be. Never get rid of data. That is the principle right now, because data is very valuable. Once the data is gone, you don't get it back. So that's why there is a new term called data lake. It's where you dump all your data in. So moving on to our current topic, Hadoop administration and DevOps, where where do we come in? Where does this session come with respect to data lakes and big data? So all these tools need deployment, management, and monitoring. So initially, to deploy on, let's say I have 100 node, I have 100 machines or 100 servers or 100 nodes. I need to deploy the stack which I use. So this can be done using Ansible, Chef, or Puppet. This can be done using management tools such as Ambari or Cloud Run Manager, or you can install them manually one by one, or you can have a container-based installation. So all these things, if doesn't make sense to you right now, let it be. I'm just giving you examples. So you can have n number of ways of deployment. most companies or organizations have a mix of these four things, these three things. Ignore the manual part. Nobody does that except for developers when they're testing out things. Uh, it's a combination of using some framework to deploy along with a manager to manage it, and and to be using some tools to monitor it. So moving on to management, you can use Ambari or Cloudera Manager Director, or you can use MapR's Manager. There are tools for management. We'll be looking at Ambari and Cloudera Manager in detail as we progress. Also, for monitoring, you can use Ganglia, Nagios, you can use Zabbix, or you can use Elk. Elk is Elasticsearch, Logstash, and Kibana. It's a combination. There are things called beats, beats which listen to whatever you're doing. You can detect anomalies, see if your node is healthy, see what is going wrong. All those things can be done through Elk. So this is the basic, the three major things about big data DevOps or Hadoop administrator. So it's a big data DevOps is the blanket term, and Hadoop administration is more specialized. So this is, as I talked about before, the data lake. This is a very high level architecture of the data lake. So the red part, which I'm going to talk about, is the Hadoop distributed file system, where we store all the data. And you can see there are, 5 green boxes. Look at the bottom part, there's data management. On top of that, there's the data access layer. Just looking at your question, you have asked me. So thing is, Cloudera is a Hadoop management software, deployment and management software, and CentOS is an operating system. So both are not relatable. So mostly enterprises use Cloudera or Ambari on top of RHEL. People don't use CentOS actually. You use the because you get support for RHEL, these things. I didn't quite get your question actually. Could you just rephrase it, or if you're asking which software we are. Cloudera Manager or CentOS. See, Cloudera Manager or CentOS are not similar. CentOS is an operating system, and Cloudera Manager is a Hadoop manager. So we are going to, in this session, we are going to talk about, in later sessions, we are going to talk about Cloudera Manager and Ambari, how we are going to, get a feel of it, how you can do automated deployment, how to manage Hadoop clusters. We'll be doing it on CentOS machine or an Ubuntu machine. It depends on what VM we have at that moment. Doesn't matter actually, it's all the same. So coming back to this, as I said, the 5 green boxes. Today we are going to talk about the data management layer, that is the Hadoop distributed file system. On top of that, we have the data access layer with the various frameworks and the services, all the daemons running. You can have Pig, Hive, HBase, Spark, Yarn, all those things running. On the left, you can see the data integration or governance tools like Falcon, Flume, Scoop, and all. On the right, you can see the various security modules such as for Kerberos, then Knox, then there is Sentry, then there's Ranger, all those things. On operations front, you have Cloud Manager, Ambari, and Zookeeper, all those things. So you can use Uzi for scheduling, all those things. This was taken off the Hortonworks website, so this shows only their tools. But if you there are a few more, for example. As I mentioned here, for managers, they have listed only Ambari, but there's also Cloud Manager, which we will be talking about in the later sessions, of course. So today we are going to give a brief of the Hadoop distributed file system. So traditionally, how we used to do, I'm going to use a very simple example and show you how we used to do things traditionally and how we are doing it right now. So let's say that you have a crossword puzzle and you need to solve it. So let's say you have 4 friends who are going to help you solve it. How do you actually do it? How do you go about doing it? You ask your friends for answers and you fill in the crossword puzzle. So that's how traditionally we do it, right? There's like, let's say that there is 5 across and there's a question there. You ask your friend, okay, what could be the answer for this? Then if that person, he or she knows the answer, he or she will let you know and you'll fill it up. So that's how traditionally we used to solve that's how we solve crossword puzzles, and this is how traditionally we store data or pre-process data. We collect the data and we put it in a central server, we process it. This has to be changed and has changed. Now what we do is we have a more distributed approach. Let's say you have a crossword puzzle. Instead of you collecting all the answers, you cut the crossword puzzle into pieces and you give it to your friends to solve. Let them solve the crossword puzzle. So this, you distribute the work to your friends. You are not a bottleneck. Previously, you could only ask one person the question. You had to collect everything, and you process it. So you were the bottleneck. So there is no bottleneck here. And also, this assumes that everyone knows the answer to everything. This example works like that. So right now, different from the traditional way, we distribute the work and we get it done, and we collate the data. We don't bring the data to a central server and process it anymore. We distribute the data across the nodes of the cluster or across your friends in this example, get them to work on it, and we go about solving our crossword puzzle. Let's see how this works in an HDFS. So let's how we going to store the data on an HDFS, Hadoop distributed file system. Okay, let's say that I have a file which is 1 GB in size. When you're storing it on the HDFS, what we do is we split it into blocks. We split it into any number of blocks. In this example, I have 4 friends. So I split it into 4 blocks and I give it to them for storage. So we can excuse me. So I have 1 GB file. I split it into 4 pieces and I let my friends store it. So this is how traditionally we store data. Moving on, let's say that I give the data to my friends and there's something happens. Okay, so one of my friends is not picking up the call, or he's not talking, or he's not well. So what do? You lose one chunk of the data, right? So in order to form a file back, you need that chunk, you need the piece A. So how do you mitigate this solution? So make copies of it. This is called replication in Hadoop distributed file system. So rather than just one person having one block, you have a copy of it. So previously, this person used to have A, B, C, and D. Now, this person has a copy of A and C, B and A, D and C, and B and E. So if any of these no, this is just an example I'm showing. There's no maximum size for any file on HDFS actually. So I'm just showing you how how you recover from node failure. Um, so you have replications of the blocks. So as I said before, you have 1 GB file. You split it into 4 pieces of 256 MB each, and you give it to 4 people or 4 nodes. And in case one major thing about Hadoop is we run it on commodity hardware, right? So we don't try to avoid failure. We expect failure and we make do with it. Like we tolerate failure actually. So this is one way of tolerating failure. So rather than keeping just one block with one person, you give them multiple copies. So let's say if A goes down, so the block C and block A are missing from A. So we can easily get that this block A is here and block C is with this person as well. So we never lose the data. And this is, here the replication factor is just 2, as in there's 2 copies of every block. Traditionally, we keep it as 3 or higher, such that, and there are block placement policies as well, and all those things are there, which will be handled in the later sessions. So in this example analogy, you are the master node or the name node in a Hadoop distributed file system, and your friends are the worker nodes or data nodes who actually store the data. So any questions? That was a very brief introduction into Hadoop distributed file system. Any questions, guys?